Hückel's rule. Have you ever wondered why some cyclic compounds like benzene are unusually stable and beautifully symmetric? The answer lies in one elegant concept of chemistry, Hückel's rule. Let's decode how this simple rule helps us identify aromatic compounds, the most stable rings in organic chemistry. Introduction to aromaticity. Aromatic compounds are special. They show exceptional stability, delocalization of electrons, and a characteristic ring-like electronic cloud. But not every ring qualifies as aromatic. To be aromatic, a molecule must meet 4 essential criteria. The 4 criteria for aromaticity. Criterion 1, the compound must be cyclic. The atoms should form a closed ring so that the pi electrons can circulate continuously. Criterion 2, the molecule must be planar, meaning all the atoms lie in the same plane. This happens when the atoms are sp2 hybridized, allowing overlap of p orbitals. Criterion 3, the ring must be completely conjugated, meaning every atom in the ring should contribute a p orbital for pi bonding. And finally, criterion 4, the ring must obey Hückel's rule. It should contain a total of 4 n plus 2 pi electrons, where n is equals to 0, 1, 2, 3, and so on. Understanding the 4 n plus 2 rule. The magic number 4 n plus 2 defines aromaticity. If a ring system has 2, 6, 10, 14 or 18 pi electrons, it follows Hückel's rule and is aromatic. But if it has 4, 8, 12 or 16 pi electrons, it breaks the rule and becomes anti-aromatic or non-aromatic. Let's understand this with some examples. Our first example, benzene. It's cyclic, planar, and fully conjugated with 6 pi electrons from its 3 double bonds. Substitute n is equals to 1 in Hückel's formula. 4 n plus 2 is equals to 6 pi electrons. Perfect match benzene is aromatic. This is why benzene is exceptionally stable and often serves as the benchmark for aromatic compounds. Next, let's take pyrrole. It's a 5-membered ring with 1 nitrogen atom that donates a pair of electrons to the conjugated system. Total pi electrons? 6. Again, 4 n plus 2 is equals to 6 pi electrons, with n is equals to 1, hence pyrrole is aromatic too. Even though it looks different from benzene, it follows the same electronic rule of stability. Now, consider cyclobutadiene, a 4-membered ring with 2 double bonds. It's cyclic and planar. Yes, but it contains only 4 pi electrons. Plug that into the formula for n plus 2 is equals to 4 doesn't fit for any integer n. Therefore, cyclobutadiene violates Hückel's rule. It's non-aromatic and actually quite unstable. Finally, look at 1,3-butadiene. It has conjugated double bonds, but it's not cyclic. That means electrons can't delocalize in a closed loop. Even though it's planar and conjugated, it fails the first criterion, hence non-aromatic. So here's the big picture. Aromatic compounds must be cyclic planar, fully conjugated, and obey the 4 n plus 2 pi electron rule. If any of these 4 conditions are broken, the compound loses its aromatic character, becoming non-aromatic or even anti-aromatic. Quick quiz. Let's test your understanding. Which of the following follows Hückel's rule? A. 4 n plus 1 pi electrons. B. 4 n plus 4 pi electrons. C. 4 n plus 2 pi electrons. D. None of these. Got it? The correct answer is option C, 4 n plus 2 pi electrons. So there you have it, the elegant simplicity of Hückel's rule. A single equation that predicts aromaticity, stability, and the beauty of molecular symmetry. From benzene to pyrrole, Hückel's insight helps us see chemistry not as chaos, but as structured elegance. Thanks for watching. And remember, aromaticity is where mathematics meets molecular art.